Okay. So here's a corollary of the existence of spanning trees, not normal spanning trees, any spanning trees in connected graphs. As a very pretty little thing, quite a sweeping statement and a very, very pretty one-line proof each direction. And it says that if G is connected, a connected graph, obviously, then G is a tree if and only if G has one edge fewer than it has vertices. Okay? So we're considering connected graphs, any connected graphs, and we're asking when is a connected graph a tree? And the answer is exactly when the number of edges exceeds the number of vertices by 1. So a tree on n vertices has n minus 1 edges. The interesting bit is the converse is true as well for connected graphs. So why does a tree on n vertices have n minus 1 edges? Well, the proof is simply consider the vertex enumeration, which we noticed exists for all connected graphs, which keeps initial segments connected. Right? So you enumerate the vertices, vertex 1, 2, 3, 4, 5, and for every n from 1 to the order of G, any n in between, the subgraph of G spanned by the first n vertices is connected. Such an enumeration exists for every connected graph, as we have seen. And then when you use that, and you're also assuming that the graph is a tree, well, then the next vertex, Vn, can send only one edge to whatever the first vertices Vn up to Vn minus 1 span in G, because if it sent another edge there, since this initial segment here induces something connected on G, there'd be a path from one of these two vertices to the other, and we'd have a cycle, and we don't have a cycle in a tree. So that was easy. How about the other direction? There's a one-line proof for that. Here it is. That's an abbreviation. And it's so short. Can any of you to whom I haven't told this proof over lunch think of that short line? Well, remember, I'm selling you this as a corollary to the observation, which was part of theorem 151, that connected graphs have spanning trees. So here's the proof. We're now assuming that the graph has, say, n vertices and n minus 1 edges, and that it is connected. And we want to show it's a tree. Well, it's connected, so it has a spanning tree. A spanning tree has many interesting properties. One of them is it's a tree. And this tree has n vertices. And therefore, by that, it has n minus 1 edges. But those are all the edges of G. So G contains a spanning tree that uses all its edges. So G is that spanning tree. G is a tree. Isn't that pretty? End of proof. I love that proof. It's really, really short and lovely. Okay, Questions about the first little bit? Okay, then on to the next little bit. Equally pretty, but a little more substance. So I gave you a slightly more complicated proof of the existence of normal spanning trees and connected graphs than necessary. And the reason I gave you that slightly more complicated proof was that it applies to countably infinite graphs as well. You can adapt it very easily. There was this one bit where we said, well, take a maximum, the maximum of that chain of neighbors of a component, and that might not exist if we're clumsy, but you can easily adapt it to infinite graphs, and that's indeed what happens in chapter 8, not in this course. But that's why I gave you that proof. Here's a shorter proof. And the shorter proof is also very edifying and interesting. And it's by induction on the order of our connected graph. And now we want to show it has a spanning tree. And it starts by saying, delete any vertex. Okay, then you can use the induction hypothesis on G minus that vertex. What does it say? It says that, well, it says that if the graph is connected, then it has a normal spanning tree. Now, obviously, G minus that vertex, let's call it V, needn't be connected, but it has components, and the components are connected, and they're still smaller than the original G, so we can use the induction hypothesis on these components. So they have normal spanning trees. And what do we want to do now? We want to put them together to find a normal spanning tree of G. How do you put them together? To make one spanning tree. Well, there's no edge between the components. So you have to join V to every component. There's no other way. You can't join V2 by more than one edge for the same reason as here, if you want to retain a tree or make a new tree. Then, well, you have to join V by exactly one edge. And now here's a problem. Will the resulting tree, for your favorite clever choice of that one edge, be a normal spanning tree of all of G? Yeah, there's one person in favor. Any person who doubts that obvious statement? Yes, one doubter. So we have 1 for, 1 against. Can you all scratch your ears or beards or heads or beam and be positive? No? Well, there is a problem. So no matter, well, not no matter. So this V might send an edge there, for example. Okay, then we have a problem. If we use that edge, we have a problem because that turns this tree upside down when we use the combined tree with this as root. Right? Because when you use this as root, then suddenly this vertex here is less than that vertex, or is less than that vertex. But it's G may have edges here that join vertices that are comparable in that tree order for the normal spanning tree of the component. But these two vertices, n vertices of some other edges of G, may no longer be comparable to the induced ordering that comes from the new tree order of the combined tree induced on C or not induced on C, it doesn't matter. So you might have suddenly incomparable edges incomparable vertices joined by an edge of G, which are not allowed. So you might say, okay, maybe we chose this edge badly, but maybe it's the only edge. Or maybe there's another edge here of G, right? And there's no way to get it right if this was the root here. So the only way to join that deleted vertex and to maintain the tree order is to connect it to the root. Then everything is fine. So if we connect it to the root here, connect it to the root there, then the tree ordering induced on the components by the combined tree will be the original orderings here, because a vertex here is less than another vertex if it lies on the path from here to there, but then it also lies on the path from here to there, and vice versa, yeah, because every path from here to anything there has to go through that root. So everything is fine, except there's one thing not quite so fine, and that is that these edges might not exist. And then we're really, really stuck. And here's where the brilliant idea comes. And it says, well, wouldn't it be nice if we could choose a neighbor of the deleted vertex and specify that this must be the root of the new normal spanning tree in the component? So this calls for strengthening of the intended assertion. The intended assertion is every connected graph has a normal spanning tree finite. And now we're strengthening that in order to overcome this little problem by saying for every connected graph and every choice of a vertex, there exists a normal spanning tree in that graph with root that vertex. That's a stronger assertion. And if that assertion can be applied in the induction hypothesis to this component, then we're fine, because we're choosing that vertex to be a neighbor of V. And there exists some neighbor of V because the whole graph is connected by assumption. Yeah, fine. But now, obviously, we have a stronger assertion. So we have a stronger, a more ambitious task. We have to show not only that there exists a normal spanning tree and delete any vertex and apply whatever to the components, the induction hypothesis, but what we have to prove now is that for every choice of any vertex, there is a normal spanning tree with that vertex as root. We have to prove more as well if we want to assume more in the induction hypothesis. But we can, because we just pick that vertex arbitrarily. And we can now say, okay, if somebody prescribes a vertex that has to end up as the root, just delete that vertex. And this is how the theorem that I gave you was born. For every choice of a vertex in a connected graph, there's a normal spanning tree with that vertex as root. Proof, delete that vertex, and apply induction. Yeah, so that's it. Now that's a very, very nice little proof. Yeah. Okay, any questions? Good. Then on to the next section, bipartite graphs. So a bipartite graph is any graph whose vertex set has a partition into two sets. And when I say partition, and I'm not giving you any particular warning, I always mean that the partition sets shall be non-empty. So a graph is bipartite if there exists a vertex bipartition such that all the edges of the graph run between the two classes, not inside a class. Okay? Graphs that can be displayed like that are called bipartite graphs, bipartite graphs. Yeah, so there's a little aside which I can't resist telling you. This is not the original word. So the first graph theory book was by a Hungarian, Dennis König, who wrote it in German in the 1930s. And he invented the lovely German word, adjective, Paar. Der Graph ist Paar, with a small p. If this. And then this got translated into English, and obviously there might have been a creative translation of that lovely little word, Paar, which König invented, but there wasn't. So people used bipartite, I think the French did as well. And then, as with all good things and all bad things too, things got re-imported into German from American English, and now this is how everybody in Germany now calls these graphs Bipartite. Okay, so you can do either. That's the definition of bipartite graphs. Here's an example, and I'm asking you whether this graph is bipartite or not. Let me just give it not so many edges. Right, so think of this as a belt, right, like this, with three edges, three rungs, or a circular ladder or something with three rungs. Is that a bipartite graph or not? Any votes for and against? Who's for? Yeah, 1, 2, 3. The other 57 are undecided. Who's against? Yeah, more. You have the majority. So any reasons? Oh yes. Why is it not bipartite?
I thought because we have these two vertices that are not connected, so this would be kind of one part. But if you look at the other vertices, like this one up and then to the right. No, down.
So what are you trying to do?
I was just trying to get one part.
Yes, but there are many, many ways of creating that part, and you always have to say log, which means without loss of generality. I'm choosing my first partition class like this or like that, and it doesn't matter because they're all of the same type, and then I get a contradiction. That's a possible proof, but a long-winded one and complicated proof. There's a simple proof why this isn't bipartite. It isn't. Why not? Can somebody give a very short proof? Okay, here's a short proof. It contains this little subgraph. And that subgraph, just look at that subgraph. If there's a bipartition, it will have to induce a bipartition of that subgraph with the same property. So induced, or yeah. And this is a triangle, right? So every two vertices are adjacent. So no two vertices can appear in the same class, but we're not allowed three classes, we're only allowed two classes. So the existence of this triangle precludes forming the desired bipartition, so the entire graph cannot be bipartite. Okay, so let me turn the ladder into a Mobius ladder. So it's still the same ladder, but we're not attaching it like this, but like that. Is that bipartite? Yes. Obviously, it must be. So here's a bipartition. I'm telling you the bipartition. It was really, I worked all night working that out, but now I've got it. And I'm showing you the bipartition, and now for you, it's easy to check that it witnesses that this graph is bipartite. There is no edge between vertices of the same color, so we can use the color classes as the partition sets. And that shows that this graph is bipartite. Okay, next example. How about this graph? What do you think? Who's for? Is it bipartite? Yes? Okay, yeah, it is. And there's an easy proof. In fact, they're all the same graph. If here are all the edges, and this is the graph K33. Isn't that amazing? So one graph comes in 3 different guises, and you won't recognize it. It's all the same graph. Okay, so let me get back to this selling aspect. I said I worked all night to find this coloring, this bipartition, but now it's easy to sell you this bipartition as witnessing that the graph is bipartite because I'm telling you the classes, and all you have to do is check that there are no edges between like-colored vertices, and that's easy to do. Yeah, so you have to look at every pair of vertices at most once. Looking at all the ways of bipartitioning the vertex set is a much more complex task, especially when 3 equals 1,000, right? So bipartite graphs have these certificates for being bipartite, which come in telling you the bipartition. They also have certificates for being not bipartite, which is our next theorem. And I think it's called proposition 161. And the proposition claims that whenever a graph is not bipartite, there's also an easy-to-spot certificate. It always exists. The existence of these certificates, which I'm going to tell you in a moment, is the content of that proposition. And what are the certificates? Well, here in the previous incarnation of this graph, the certificate was a triangle, right? Slightly more generally, odd cycles are clearly not bipartite, right? So if you have only 2 colors, you take a long cycle, you have to color the first 2 adjacent vertices differently, and then this one has a color that cannot be used on that, so you have to use that color again, and on this you have to use that color again, and so on. So you have to alternate colors, and when the cycle is odd, it doesn't match up at the end. You'll end up with 2 equally colored vertices that are adjacent. So this is a log proof. So odd cycles are easily shown to be not bipartite, and the proposition says that a graph is bipartite if and only if G contains no odd cycle. Right? And the proof of the forward implication is easy. Right? If it had an odd cycle, then that would inherit a bipartition, but it can't. Odd cycles cannot inherit such a bipartition because they're themselves not bipartite. How about the other implication? Pick any spanning tree in every component, right? So, or assume the graph is connected, find a bipartition in every component, and then put the bipartitions together. So, pick a spanning tree, and, yeah, okay. All right, and then just pretend the graph, pretend that's the graph. That's a bipartite graph. Why? Well, you just start coloring it. Pick any vertex, give it color 1. Then the neighbors clearly have to get color 2. Then the neighbors of those have to get color 1 again, but that's fine because you're a tree, so they're not adjacent to that. We colored all the neighbors of this vertex blue, and sorry, I used the tree fact in that this is an independent set. Right, there's no edge here. Right? So we can color all the neighbors blue because we did. The neighbors of those blue neighbors are now not themselves adjacent to this because otherwise they would have been in the first set. So we're coloring them all yellow. And, yeah, so done, and then color all their neighbors blue again, and so on. So we just alternate as we're moving out from our first colored vertex along the tree between colors. And that is indeed a coloring of that tree. Right? There are no edges between like-colored vertices because they would create a cycle in that tree. Right, and now the claim is that if our graph doesn't have an odd cycle, then that is actually a coloring of the entire graph. This bipartition works for G, not just for the spanning tree. And why does it work for G? Well, suppose it doesn't. Suppose there's an edge between like-colored vertices in G. Well, but since they're like-colored, the path in T between these has an even number of edges. All right? And then plus this edge would be an odd cycle in G. And that doesn't exist. I think that's pretty amazing, especially because we started with any spanning tree. Right? It could have been a completely different spanning tree. That would have produced a unique bipartition. This once the tree was chosen, produced a unique bipartition up to renaming the classes. So every other spanning tree also produces a unique bipartition, unique depending on the choice of that tree. So maybe there are more than one partitions, but in an ordinary day-to-day type bipartite graph, there's unlikely to be more than one partition. Many bipartite graphs have only one partition that works, So all the different spanning trees give that same partition. Isn't that weird? I think that's pretty amazing. So think about it. Okay, questions? Maybe there was a mistake here. No, there wasn't. Not an intended mistake. Right. Any questions about unintended mistakes? No, good. Okay, that's that. Change of topic again. I'm going to give you two more relations on graphs. So we had two relations, subgraph and induced subgraph, right? And induced subgraphs are, in particular, subgraphs. So let me write this sort of very informally like this. You can make it formal by considering relations as sets of pairs, and then that becomes true. So, but I don't want to be formal. So the induced subgraph relation is a special case of the subgraph relation, and I'm going to give you two more. And they look rather similar, so I put some letters on the first to make them look less similar. And those are the four relations between graphs that are often considered. There are others. In particular, we can weaken this relation just a little bit more to make another interesting relation that has long been disused. It was found and used by Klaus Wagner, whom you will meet again later in the course. So he has a weakening of this relation, which is going to be called the minor relation, graph-minor relation. But that's been forgotten. You can look it up in his work. Okay, so let me define those. First, these letters are TOP, and they stand for top, and top doesn't stand for opposite of bottom, it stands for topological. Okay, so what does that mean? Okay, consider a graph X and now change it by inserting on some of the edges of X some new vertices, like this, for example. Not necessarily on all of them. All right, so this bigger graph is a Tx, where T stands for topological again. It's, and I'm saying it's ATX, which is very, very bad notation. So Tx, when X is a specified graph, Tx is not a specified graph. It's one of many graphs. It's one of all the graphs you can obtain by putting subdividing vertices on the edges of X. So this is really a class of graphs. Never mind. Right? So this is called a subdivision of X. Subdivision of X. Okay, and if that is a subgraph of some big graph Y, so there may be more in Y. Like that. Then we say that X is a topological minor of Y. Right? So, once more, what does this mean? In words, X is a topological minor of Y means that Y contains, as a subgraph, some subdivision of X. And now mark the use of the word some. It always signifies an existential statement. Right? There exists a subdivision of X which is a subgraph of Y. Okay. And of course, the T comes from the fact that when you consider these as topological spaces, then they're the same spaces, they're homeomorphic, no matter how many times you subdivide an edge. Okay, questions about that definition? Yeah?
Not the definition, but in general. You said it's hard to find the partitions on bipartite graphs.
Okay, back to bipartite graphs, fine.
Yeah, because I was wondering, is there actually an efficient way to find the partitions? Or to, if there exists any partition?
Yes. So, okay, let me just underline that or underscore that these are very different questions. So you asked, is there an efficient algorithm, no matter what efficient means now, that's not part of this course, is there an efficient algorithm that decides whether a given graph is bipartite or not? And so, for example, you might try out all the bipartitions and see whether they work. That's not efficient. You might look for all the cycles. Yeah, but how do you look for cycles? Then you have to look at all vertex sequences and see whether there is cycle and then see whether they're odd. Also not so efficient. So that's a good question. Is there an efficient algorithm that decides whether a given graph is bipartite? What I tried to give you earlier was something weaker. That was the assertion that there exists an efficiently checkable certificate for being bipartite, namely the bipartition, and there also exists in every non-bipartite graph an efficiently checkable certificate for not being bipartite, namely an odd cycle in it. So it's easy to point out a cycle, and then it's easy for you to check that it's odd, and so that is something less ambitious than deciding whether the graph is bipartite or not. And for the computer scientists amongst you, the first is the decision problem, and if there are efficient algorithms that determine whether an input graph is bipartite, then that means that bipartition is in the class P of problems, and the latter certificate thing just means that being bipartite is in NP. Okay, end of brackets. Doesn't belong here, but you can maybe discuss it in the exercise classes and ask them the same question. So I didn't answer your question. I didn't say whether it was in P or not, but I just pointed out the difference between the two questions. Yeah.
I have two questions about
Yes.
the
Definition here.
last definition. How would you read the last statement out loud? X top Y or?
X is a topological minor of Y.
You have to say, okay.
Yeah.
And the second question is,
I could also say Y contains a TX. It contains a TX.
okay. And the second
Contains, right? Contains as a subgraph a TX, some TX.
Yes, okay. And is X already a topological minor of TX?
Yes. Yes, y doesn't have to be bigger than tx. Y can be equal to this tx. Yeah, good. More questions? Yeah?
So x itself also counts as a tx?
Yeah, yeah. X itself counts as a tx, and it can also be taken as y. So x is a topological minor of itself. Yeah. Okay, so next one, this one here. That reads minor, is a minor of. So let me start like this. We start with a graph. That has some edges. And this graph, call it x again. And now we do something to that graph, just as we did here. And what we do to this graph now is every vertex of this graph, we blow it up to some connected graph. And then, whenever we see an edge of x, we add at least one edge between the two connected graphs that replaced these vertices. Maybe more than one. And then, this graph here, I should have done it in blue. Oh no, in yellow. I should have done it in yellow. Okay. So now that's much clearer, isn't it? And that is called an IX, in analogy to the TX. And I stands for inflated. So you take every vertex, there were 4 vertices of the original X, and you blow them up to some connected subgraphs. These connected subgraphs. And then you put in some edges. And I'm not telling you which edges exactly you can put in. What I did tell you was that whenever you saw an edge of X, you had to add at least one edge between the two corresponding connected subgraphs, corresponding to the two end vertices of that X edge. And in order to get an IX, an inflated X, you're not allowed to add edges between these connected graphs where you didn't see an edge of X. Right? Any graph obtained in this way, no matter how large these connected subgraphs are, what exactly they are, trees or triangle, anything, all these things are called IXs. Okay? And if an IX is contained in a big graph Y, so right, but there may be more vertices in Y then we say that X is a minor of Y. And we write this. So once more, X is a minor of Y if and only if Y contains, as a subgraph, some inflated X, some IX. Y may have such edges here. Okay. So it helps to think of this process backwards. So when X is a minor of Y, so in other words, when Y has a subgraph that's an IX, then we get a map from a subset of the vertices of Y, namely those that occur in the embedding of the vertices of the IX. There's a map from some of the vertices of Y to the vertex set of X. Namely, for every little vertex, you look, well, the map is defined only on those vertices that live in the IX, that is a subgraph of Y. And for those vertices, you just map that vertex to the vertex of X that gave rise to the connected subgraph it's in. Okay, so that's an onto map, a surjective map from a subset of the vertices of Y, all those that are not blue, to the vertices of X. And obviously, it's not any such surjection, but it's one where the edges are right. So whenever X has an edge between two vertices, then the inverse images of these vertices under this map, what are the inverse images? The inverse image of this vertex is that set, not true, that set. And the inverse image of that vertex is that set. There has to be at least one edge between elements of those inverse images. Okay, so it sometimes helps to think of minors in terms of this map. Right. Topological minors are minors. I'll show you that in a moment. Let's first check that first two special cases. If we No, they come in a moment, these special cases as well. So let's prove, or indicate a proof, that these are orders. Right, they are reflexive, symmetric, and transitive. So reflexive and antisymmetric are trivial, so why are they transitive? Okay, let's look at this first, transitivity. If we have a graph and we subdivide it, so this is a topological minor of anything that contains this, for example, and then this bigger something. We subdivide that, for example, like this, then the result will contain a subdivision of the original subgraph, the white graph that we started with. Right? We have lots of junk that we're not interested in, and we may have inserted some subdividing vertices in addition to the yellow ones, or also on the subdivided edges of the original graph X. So if X is a topological minor of Y, and Y is a topological minor of Z, then X is a topological minor of Z. Okay? I mean, we could do this more formally, but that would just be very, very boring. When you check it, you have to do it sort of formally in your head, but that's fine. Okay? Right. So how about this relation? That is not very nice. But, okay, so let's think of X being a minor of Y being a minor of Z. So what does it mean when X is a minor of Y? It means that the graph Y has a subgraph which is an inflated X. All right, so X maybe has two vertices and an edge. So the inflated X will now be such a graph here where this vertex is expanded to that yellow thing here, which is a connected subgraph of Y. And this vertex is expanded to just a one vertex subgraph of Y. They're both connected. Both the yellow little eggs there are connected. And there has to be at least one edge to represent this edge. So maybe they're both there. Right. So that's what it means that X is a minor of Y. And of course, there may be some other stuff here as well. Now, Y is a minor of Z. So inside Z, we can find an inflated Y. So the inflated Y has for every vertex of Y some connected set. So there are three more here. Something like that. Right? For each of these three vertices, I'll find a connected subgraph of Z, all nicely disjoint. And whenever I have a red edge here in Y, there has to be at least one edge of Z between the corresponding connected subgraphs. Okay, and now, and maybe Z has other stuff as well. Okay, and now the claim is that X is a minor of Z. What do we have to show? We have to find for every vertex of X a connected subgraph of Z. And these have to have the property that whenever we have two vertices of X that are adjacent, then there's an edge of Z running between the two connected sets. Now, which connected sets do we take? Well, easy. We just look at these two maps that I told you earlier, and then we take the inverse images under these maps. So every vertex here expands to a connected graph there, and that gave rise to a surjective map from a subset of the vertices of y to the entire vertex set of x, with the property that for every vertex here, the inverse image was connected. And we use that map and take as, for a little x here, the inverse image under this map, that is this red dot, and it has certain vertices in y, and each of these had an inverse image in here that was connected in z, and an edge between any two such inverse images of vertices of y that are adjacent. And we need this adjacency because that was part of the requirement for x being a minor of y, that there's an edge here that makes this yellow blob connected because it's an expansion of this x, right? And then f composition G, f after G, can be used to witness that x is indeed a minor of z. So the pedestrian way, once more, is to say, look at any vertex of x, it expands to something connected here. Every vertex of that connected subgraph of y expands to something connected in there, and between edges here that make it connected, there are corresponding edges there, and then the collection of connected subgraphs here is connected to make one big connected subgraph there, which is the expansion of that vertex. It's completely trivial, it's just a bit of a mouthful to say. All right, but it's good to remember. Okay, questions? Yeah.
This feels like when we have a set x and we say that x is a minor of y, it feels like we're saying there's a homomorphism, but not really.
Yeah. Good point. Homomorphisms are sort of related, but not in the way that you would like them to be related. They're more like the opposite.
Because we cannot map to the points, but we have to map to the points?
Well, homomorphisms, for a start, have maps the other way,
Exactly.
from x to y. And the requirement is that they preserve connectivity. So, so I gave you the definition of homomorphisms, and you can study how they're related, and the answer is they're hardly related. But it's very important to be clear about that. Yeah. Mm-hmm. Other questions? Okay, then let me just wipe the board and give you some more properties. So first observation is 172, which says that x is a minor of y if and only if x can be obtained from y by deleting or contracting edges and deleting vertices. Right, what does contracting an edge mean? It means that you take two adjacent vertices, say little x and little y, and you put one vertex there instead. I'm calling it vxy now, and you make that adjacent to all the neighbors of either x or y in the rest of the graph. So this new vertex will get adjacent to this vertex because this is adjacent to both x and y. It will also be adjacent to that vertex. Let me just write it like this, because y is adjacent to that vertex, and it will also be adjacent to this vertex because x is adjacent to this vertex. All right? So if this is G, then after contracting, we get G contract E. E is the edge xy. Or we could also write G contract xy. Xy is just notation for an edge, right? And then the contracted graph is a minor of the original graph, right? This combined vertex expands to a connected graph in G, namely a K2. And all the required edges are there. Right, so that's edge contraction. And edge deletion you know, vertex deletion you also know. So the assertion of 172 is that when you have x a minor of y, then you can obtain x from y by deleting and contracting edges. And how do you do it? Well, by definition, you know that y has a subgraph. I'll take a deep breath and say delete everything that's not in that subgraph. Delete everything blue. I'm using deletion now. That is an inflated x. And now contract all the edges that are inside the same inverse image of a vertex of x. And these inverse images, by the way, these yellow blobs here are called branch sets. Branch sets of the Ix. Right? And an Ix that is a subgraph of y, or not, and any Ix is called a model of x, a minor model. Right? An inflated x or a model of x in y. Has nothing to do with model theory. Right? Okay. So let me just write that there. X is a this thing here, this Ix, is a model of x in y. Okay, and we also call x a contraction minor of the Ix. Remember, we first deleted stuff, vertices and edges. In particular, this blue edge here had to be deleted as well, so that we could get our inflated x inside y. We had to delete some vertices, the top vertices there, and this one. And then we also had to delete this edge, because with that edge, what we had left wouldn't have been an inflated x. And after this deletion of some vertices and some edges, we'd be left with an Ix, a model of x that used to be in y. And now we contract. And which edges do we contract? Edges that join vertices in this model that lie in the same branch set, right? The same connected subgraph of y that is expanded from one vertex of x. These are called branch sets. And here, the original vertices of x are called branch vertices of the Tx. Branch vertices and branch sets. Right. So I try to persuade you that if x is a minor of y, then you can indeed obtain x from y by deleting vertices and edges and contracting edges. Right? One has to think a little bit about this contraction. When you contract all the edges in a branch set, you really do end up with just one vertex. And the edges that you end up with, which are yellow edges here, are precisely the edges that you're supposed to have in X. No more and no less. No more because we deleted any other edges that we didn't want to filter through to X. Okay. So the more interesting aspect of 172 is that the converse is true. Well, not more interesting. It's equally easy. So the converse is true as well. If you delete a vertex or you delete an edge, then you're taking a subgraph, right? And subgraphs are, in particular, examples of minors. And when you contract an edge, then you're also you're obtaining a minor, as I said earlier. So they really come to be the same thing. And often when you look at the literature and people define what minors are, they say very sort of offhandedly, a minor is any graph obtained from your given graph by deleting or contracting edges. They often even forget to say or deleting vertices. Right? But that's fine, and it works well for some induction proofs, because you can say, okay, if x is a minor of y, and we want to prove something about y, if we know something about x, or the other way around, it might be enough to prove that for these single steps of deleting one vertex, deleting one edge, or contracting one edge. But then you don't have a picture. And often to get to the proofs, you need an intuition and you need a picture. And the picture of that is that of these branch sets. So you see a fuzzy sort of version copy of X, a model of X in the big graph Y by having every vertex of X expand to something connected there. And then when you had an edge here, you have to have at least one edge, maybe many there. It's sort of helpful to think of that as minors rather than this neat and slightly slick definition of contract or delete edges and possibly delete some vertices. Okay. So the next observation, as I told you, is 173, is that topological minors are minors. Yeah. So when we subdivide this is our X. Now we subdivide some of the edges like this. Then we want to show that the graph we obtained, the Tx, is a model of X. Right? And when that Tx is contained in some subgraph, some bigger graph, then this model of X is contained in some bigger graph, and that would make X a minor of that bigger graph if X is a topological minor of that bigger graph. So we want to show that every Tx is in fact also an Ix, an inflated X. That's sort of easy, right? So we have to inflate every vertex. And we just do that by taking the incident edges and taking some of them. Doesn't matter, maybe all, maybe none, maybe one, in such a way that we eat up all the subdividing vertices. We eat up all the vertices. So for this, the branch set would have to contain everything that we didn't include the first time round, because eventually we want the entire Tx to be a model of x. We want that to be an Ix. So, yeah, and so this just sits by itself, poor thing, and that gets this. And notice that the required edges are there. So this branch set sends an edge to that branch set, as it ought to, because these two vertices of x are adjacent. Yeah, and it does here. Again, this is very informal now, and it wasn't a real proof, but making it into a real proof is easy. Okay, how about the converse? Yeah, question. No. You can do that in many ways. So here I just indicated how you can do it in different ways. Okay, how about the converse? Is when x is a minor of y, is it also a topological minor of y? No. Look, think of x as having lots of large degrees, right? If you have a Tx, they have the same large degrees. They also have some new vertices of degree 2, but they still have the original vertices, the branch vertices of the same degrees. So when x is a topological minor of y, then you can map the vertices, the branch vertices of this Tx to vertices of y, not all of them. And if your Tx is a subgraph of y, then these vertices, which inherit in the Tx the degree, the high degree they had in x, will have to have that same high degree at least in y as well. But when x is just a minor of y, the branch sets that correspond to a vertex of large degree in y have to send out many edges, namely to the corresponding branch, to the branch sets corresponding to the neighbors of x. But if this is this is a vertex in x, and that expands to a branch set in the model of x that lives in y, then in y, this branch set can send out many edges to other branch sets without any particular vertex sending out many edges. So branch sets can consist of vertices which in y have low degree. In fact, degree 3 is all you need. Right? So that's an abstraction to minors also being topological minors, but it's the only abstraction. So when x has max degree at most 3, then if x is a minor of any y, this y will also contain a Tx. And why is that? Well, if you have a branch set and you know that at most 3 edges leave it, and you know that this branch set is connected, then you can get from this vertex to that by some path, and you can get from this vertex to that by some path. And you stop the moment you hit the earlier path, maybe only there. But wherever you stop, you say, ha, that's my branch vertex. Right? So when your vertex of x expands to a connected branch set in y, then x being a minor of y means, by definition, that y contains a model of x as a subgraph, so it contains an inflated x, And let's just consider that subgraph, and let's this vertex of x had degree at most 3, so this branch set sends edges to at most 3 other branch sets. In y, it might be adjacent to some others, but we don't need those edges in order to get an inflated x. Right? We just need one between corresponding branch sets corresponding to adjacent vertices of x. Okay, and then when you have 3 such edges going out, well, they come in to this branch set somewhere, and these at most 3 vertices can be joined up in such a way that this becomes a branch vertex of a corresponding Tx that, yes, that lives inside the Ix that we know exists in Y. So if X has max degree at most 3, then the converse is true as well. Okay. Questions? No. I have 5 minutes left, so let me give you some more definitions. Sorry, there isn't very much substance today, but I think at least some of the not so substantial observations at the start are at least pretty. And this is fundamental stuff. You have to familiarize yourself with these notions. They come up all the time later, and it's, I think, best to take some time to get really clear about what minors are and play with a few examples and so on. So do take your time and look at them. So some new notions, directed graphs and multigraphs. Right, so officially, according to the notation or terminology that I gave you at the start of this course, neither of those are graphs. There's something like graphs, something, if you like, a little more general. So the idea about a directed graph is that the edges between 2 vertices have directions. And you're also allowed to have more than one. All right, so that's a directed graph. Sometimes, I'm afraid, called a digraph. So those are directed graphs. 2 vertices may have many edges between them. And how do you formalize that? Well, we used to say an edge is a 2 set of vertices. You can't do that anymore because this 2 set of vertices comes in 3 forms. 2 of them are even the same. So we have V and E sets of vertices. They're disjoint sets. A set of vertices and a completely different set of edges. Now, importantly, this is just a set, and we call them edges. You can't ask what is an edge. We just have 2 sets. And then, in addition, we have maps from E to the vertices, from the edges, from these edges to the vertices. We have 2 maps. I for initial and T for terminal. So let me write initial here. So the starting vertex from E, this is little e, we have two maps. One that assigns to E one vertex, which we think of as its initial vertex, and that's that. And we have another map which assigns to E one vertex, which we think of its terminal vertex, and that's that. And this little E prime here just agrees, or these maps agree on E and E prime. They have the same initial vertex, and they have the same terminal vertex. That's fine. And this one here, E double prime, has different images under these maps. But the end vertices are the same. Okay, so that's a directed graph. A multigraph is something like that. Oh, this is allowed as well, right? So an edge is allowed to have I of that edge and T of that edge the same vertex. So these things are called loops. So what are they? Again, we have disjoint sets V and E, and we only have one map from E to the two sets of V, just as we had it in graphs, but there may now be different edges that have the same two set. Yeah. And these maps, so are, okay, we're also allowing, let me, oh, I don't know, this is terrible. Right, okay. So we're allowing loops as well. Okay, so those are multigraphs and directed graphs. So if you like, multigraphs are obtained from directed graphs by forgetting the directions. There's also oriented graphs. Oriented graphs are directed graphs that don't have parallel edges like this. These are called parallel edges. And oriented graphs are things obtained from real graphs by orienting every edge, by giving every edge a direction. So they don't have parallel edges and they don't have loops. Those are oriented graphs. Okay, and just some conventions. When you have a loop, then your graph is not true connected. Right? That's just by decree. Otherwise, the definition of connectedness and true connected and so on, k-connected is the same. And when you have parallel edges, 2 or 3 or 17, then this is not 3 connected. So 3 connected multigraphs are graphs. Okay, just one more thing. Contracting a loop deletes it. by convention. Contracting an edge that is parallel to another edge is more interesting. So when we contract this edge here, that one, then this becomes a loop. And this becomes the contracted vertex xy. And this becomes a loop at this vertex. Right? Maybe there are many loops at that vertex. And last notion, suppressing a vertex. Vertices of degree 2. Well, what does that mean? It means that. Right? So it's undoing subdivision. It's thinking of this vertex as a subdividing vertex. So you can look up in the book how this is formalized. So maybe there are two vertices of degree 2 here, and I can suppress them one after the other. So if I suppress this, then that is still there, and it retains its degree, right? When you suppress a vertex, all the other vertices retain their degrees. Yeah, so there's one question, what do you do with that? Answer, it vanishes. Swish and flick. Okay? So if you suppress all these three vertices, then nothing is left. If you suppress one of them, you could say, if you're in multigraphs, you can say, well, we have a multigraph of two vertices joined by two edges. If you're not in multigraphs, if you're in graphs, you say, oh, well, I can't suppress it because I don't get a graph. But if you then suppress that as well, you can say, okay, I have a loop now. But that still has, it has degree 2. In a multigraph, this has degree 2. Right? It's incident with only one edge, but it has sort of two incoming edges. And then you could, in principle, you could suppress that too, and then this disappears, but that is a massless string. Don't allow that. Okay. But this is all just notation, so don't worry about it, don't learn it. If it comes up, when it comes up, you know where to find it. It's in chapter 110. And if it doesn't fit what you want to do, then you come up with new definitions. Right? Okay. So any more questions? No? Okay, thank you very much.